think. All right, let's try this again. We'll load it back up. Okay. So this is what we have. You know, in the video. I'm not going to try going back to the video again. He has white text on a black background, but the idea is, you know, 0 means there's nothing there, and 255, or a high value, represents basically ink has been put there. Okay, and so but anyway, it's just a vector of 784 values, 28 by 28. Okay, and this is what the vector looks like, and we're asking the computer basically take this vector of 784 values. Okay, take that and tell me what number is it, right? So if I just showed you 784 values, right? So as brains, like we're able to like look at a picture and we recognize stuff, right? But if we just say, hey, take these numbers, which is basically what the computer sees. The computer doesn't have a concept of vision right now. It just sees these 784 numbers. But we're asking, hey, can you take a look at that and tell me what the number is? Okay, that's what we want to do. Okay, so we know in this case the answer is, that the answer is 5. Okay, and in our training data it is labeled with 5. But what we want to do is we want to turn that into an output with 10 nodes. Okay, so to do this, I'm going to create a function called vectorize, which is going to turn everything into zeros and ones. Okay, and so this first image, which is a 5, we want it, the answer should be 0, 0, 0, 0, 0. Okay, so this is digit 0 is 0, gets a 0, 1 is a 0, 2 is a 0, 3 is a 0, 4 is a 0. And then for the 5, it gets a 1. And then, you know, this corresponds to digit 9, and that's a 0, right? So R is index starts at 1, so, you know, it might look a little bit funny. But this corresponds to the digit 9, this column, and this column corresponds to the digit 0. And so we want, for the first image, we want everything except for the column corresponding to the digit 5 to be a 1, okay? So, which means in this second row, okay, everything is a 0 except for this very first value, which is a 1, which means the second row corresponds to the digit 0, right? And so if I were to, if we were to ask, you know, show the digit for the second row in the training data, we should see something that looks like a 0. And indeed, that's what we see, right? And then the third one, this corresponds to the digit 4, okay? We've got 0, 0, 0, 0. This one corresponds to a digit 4. And so the third row should look like the number 4. And indeed, that's what we have, okay? So anyway, I've applied this and I've converted all of our training data into, our output labels, Y, into basically this matrix of zeros and ones. And we're going to use this as kind of the training data here. Okay. So I'll go ahead and we're going to start creating our neural network, and I'm going to define the sigmoid function. I'm going to define the derivative of the sigmoid function, sigmoid prime, okay? And so all of these things, these are found in your notes from Monday, okay? And then we're going to have the cost function. The cost function is going to be the difference between the actual values, which are the vector of zeros and ones, the length 10 vector of zeros and ones. And we're going to take that difference, from whatever our neural network predicts. Okay, so our neural network is going to predict a vector of length 10 with values between 0 and 1. Okay, all right, so the question is, what is the vectorized function doing again? Yeah, it's turning the label, the answer, right? So we have the answer. In our training data, we have the a matrix of inputs, and the outputs, okay? But right now the outputs are an integer. The output is the number 5, the output's the number 0, the output's the number 4. But we want to turn them into zeros and ones, okay? So we want to turn the label 5 into zeros for all the nodes except for the node with the 5. Okay, that's what we want to do. All right, here's a question. Why don't we just have one output node? And the output node goes from, okay, my computer just closed that program for no reason. But why not just have one output node and just have that output node go from, say, you know, the output of the output node be the number, right? Like we can always, you know, scale things up and things, but, you know, why not it just say like, if the number is a 9, make it a 9. If the number is a 5, make the output a 5. Or if the number is a 1, make the output a 1. Why not do that? Why do I have to do this if it's have 10 nodes, make everything else 0 and the one that it is a 1? So technically, couldn't you do that by adding the output layer as a hidden layer and then the output, real output's a max of this? I mean, I could have another step, but you know, as far as the neural network goes, why not just have 100, you know, 784 in the input layer, you know, however many in the hidden layer, and just one node in the output layer? Why am I having this? Why do I have to have 10 nodes in the output layer? Okay. The reason is that if I only have one node in the output layer, the way we measure how far off we are is we're using the squared residual, right? We're using the squared residual. And so let's say the true answer is 2, okay? The true answer is 2, okay? And let's say we have a model that predicts 2, a model that predicts 3, and a model that predicts 9, okay? Okay, the one that predicts 2 is correct. The one that predicts 3 and 9 are wrong, okay? However, if I use the squared residual, what it's gonna do is it's gonna say, well, 3 is only a little bit off, so it's less wrong than the 9. The 9 is more wrong because it's farther away, okay? And that makes sense if the thing we were trying to predict was like, how much money are we gonna make? Okay, that's a quantitative, that's a numeric thing, and you wanna be as close as possible. But in this case, as far as classifying a digit, okay, the digit doesn't actually represent a quantity. It just represents a category, right? And so predicting something to be if the digit is a 2 and we say it's a 3, that's wrong. If the digit's a 2 and we predict it's a 9, that's equally wrong, okay? The 3 is not less wrong than the 9. Does that kind of make sense? Okay, the 3 is not less wrong than the 9, but if we had only one node, it's going to use the distance, the squared distance, and it's going to say the 3 is less wrong than the 9. Whereas by having 10 nodes, and all of them being zeros and ones, zeros or a 1, okay, the predicting a 3 will be, we'll have a 0 for the correct answer and a 1 in the wrong spot. Predicting a 9 will have a 0 in the correct answer and a 1 in the wrong spot. But predicting a 2 will have a 1 in the correct spot and zeros everywhere else. And so the 2 will be the only one that's correct. The 3 and the 9 will be equally wrong, which is what we want in this case. And I hope that makes sense. Okay. So, so anyway, so we have 10 nodes in the output layer. Okay. So anyway, I'm going to define our neural network. Input layer, we have 784 nodes. The output layer, we have 10 nodes. And the hidden layer, I got 30 nodes, and this is just an arbitrary choice. Here I'm going to I have the first weight matrix and second weight matrix, okay? So the first weight matrix is going to be 784 by 30, and then the second weight matrix will be 30 by 10, okay? And then here I'm going to just fill it with random values between negative 0.5 and positive 0.5. So I'm doing RUnif and I'm subtracting 0.5. So everything's going to just be a random value between negative 0.5 and positive 0.5. And you know, this was an arbitrary choice, but I just used RUnif and then I just shifted all the values down by 0.5. So I get some negative and positive values. Okay. So I fill out my two weight matrices. Okay. All right, is this okay so far? All right, and then so when I actually do the training, I'm going to do something called stochastic batch gradient descent. Okay, now it's a mouthful and it sounds scary, but it's not. Okay, so let me just pull up an old slide here. Okay, so this is kind of this is our picture right now. So good guess, we want something like this. Okay. If I were try to take in my X matrix right now, which is 60,000 rows by 784, and I try to feed that through my my neural network, it would really take my computer a long time because it's got to do a lot of calculations. I don't know, 60,000 by 784. I'm not sure what that is. It's, you know, on the order of millions of calculation, millions of values just passing through. So what I'm going to do is I'm going to just randomly select 10 rows. I'm going to take that whole set of 60,000 images and I'm going to just split it into 6,000 chunks of 10 images each. Okay, and that way the training values, there's only it's going to be 10 by 784. Okay. Sorry, give me a second, my dog. In his old age, my dog has been demanding more of my attention, which is fine. But we've got, so we're going to split up this whole data matrix of 60,000 rows into 6,000 chunks of 10 rows, okay? And then I'm going to use that to calculate the gradient, okay? So remember, the gradient is calculated by using the difference between the actual values and what our thing predicts, right? And so if I used all 60,000, I would have 60,000 actual values and 60,000, and I would have to make predictions for 60,000 things. And that's going to require a lot of calculations, okay? So I'm going to just do a small batch, okay? And we're going to do 10 rows. So we have 10 actual values, and we only have to make predictions for these 10. And based on the 10 actual values and the 10 predictions, then we calculate a gradient, which might not be the exact same thing as the true gradient, but it should still point either uphill or downhill in the correct way. And so just using those 10, we're going to take a step downhill. Then I'm going to take another random 10 values, okay? And I've got the 10 actual values, and then the make 10 predictions. We calculate the gradient there, and then we take a step downhill, okay? So that's the stochastic part. The stochastic is we're getting 10 random values at a time, and the batch, I guess it should be, you know, stochastic batch just means we're doing a batch of 10, okay? So stochastic batch gradient descent just means that we are going to just take 10 at a time. Now that value 10 was arbitrarily chosen. If you wanted to do 20 at a time, 30 at a time, 5 at a time, so that's fine as well, okay? So anyway, I just have some code to kind of facilitate that. That just shuffles up the 60,000 rows, and we're going to just take 10 at a time, okay? And then, and this is the training of the neural network, okay? We are going to take the 10 rows that we've selected, create our X. We're going to take the 10 actual values and create our Y, all right? And these are the vectorized things with the zeros and ones, okay? We take our input values X and we pass it through our neural network with our current weight matrices W1 and W2, and we get our Y hats based on our current weight matrices. And with our Y hats, we calculate the gradient. The gradient is going to be based on the difference between y and the y hats, okay? And then, we did the back propagation on Monday, and so we found the gradients, the delta J, dj dw2 and dj dw1. So we find the gradients, and then we update our gradients by taking our current values and then subtracting off some scalar times the gradient, okay, to take a step downhill. Take our current value and subtract off the scalar times the gradient. Okay. All right. Does this code make sense as far as training the neural network? Okay. So this is very similar to what we did on Monday, in that we do forward feed to make our predictions. We use the predictions to calculate our gradients, and then we take a step downhill. Okay. And so I'm going to go ahead and do this. I'm going to just run this once. We're going to go do all 60,000 images. And now we are done. Okay. Now we are done. And so we have some values that that we've settled on for W1 and W2. Okay. Why did I divide the values of X by 255? Okay. Oh, that's a good catch there. All right, so the reason for this is that right now the way we represent images is, we use this base 2 value, okay, from 0 to 255 to represent, how light or how dark the image is. Our neural network, because of the sigmoid function, it does not handle values bigger than, say, 4 very well, okay? If the value is 4, pretty much the sigmoid function is 1, okay? It's like 0.999 something, okay? And so, values between 4 and 255 all kind of get treated the same, all right? And so by kind of scaling everything down, just by taking that number from 0 to 255 and dividing by 255, it puts it in a range that works better with the sigmoid function, okay? Sigmoid functions, will give you distinct values, say from -2 to +2. So I could have chosen any kind of other scaling system, okay? Dividing by 255, dividing by the max of X seems like a decent choice, but anything that really puts your X values between, say, -2 and +2 will probably work well. Dividing by 255 was just simple enough, okay? But yeah, if you don't do that, then values of X, say, X equal to 10 and X equal to 200 are going to get treated pretty much the same, because the sigmoid or the logistic function just treats them almost as one. Okay, so anyway, we ran this through all 60,000 images, and now it is done, okay? So I haven't loaded any kind of special package. I haven't done anything. That we just did plain old matrix operations, addition and subtraction. I mean, doing the back propagation, this was a little bit of a hassle, but we did it on Monday, okay? All right, and so let's go ahead and let's make our predictions, okay? So here I'm gonna take our test data set, which we have not seen at all, okay? We have not seen our test data set at all. And we're gonna just run this, okay, through our neural network using the weight matrices, weight 1s and weight 2s that we have trained using gradient descent, okay? So we ran this. This was the gradient descent that trained our first and second weight matrices. And we're gonna go ahead and just do forward feed on our training data, okay? So we'll just go ahead and take our input matrix X, multiply it by our first weight matrix. We're gonna apply the sigmoid function to Z2. We're gonna take the output of that and multiply it by our second weight matrix that we've trained. And then we're gonna apply sigmoid Z3 to our Y hat, okay? And so if I take a look at just Y hat, say like the first 5 rows, this is the output here. It's kind of a mess. It looks, because it's produced all of these things. So it's going to look better if I round it. Like if I round it to say 3 decimal places, this looks a lot better. Okay. So this first row, we have really small numbers: 5 to the times 10 to the negative 5, 7 times 10 to the negative 8. So this basically just rounds off to 0, 0, 0, 0, 0, 0, 0, and then it puts a 1 here in the 8th column. So what digit does that correspond to? Okay, and the 0 everywhere else. Okay, so this corresponds to the digit 7, right? Because again, this is the 0 and this is the 9. So this is the 9, the 8. This corresponds to a 7. So, so what I'm going to do is I'm going to ask R to just tell me which column has the max value, right? So if you do, there's a function called max column, and it will tell you, oh, okay, the 8th column has the maximum value, the 3rd column has the maximum value, the 2nd column has the maximum value, so on and so forth. But because of ours doing index 1, starting the index at 1, we're going to just subtract 1. So our guesses will be the max column minus 1. So if we just take the first 5 guesses, okay, our first 5 guesses are 7, 2, 1, 0, and 4. Okay, so let's go ahead and see how well did our matrix perform. Okay, so our first guess is a 7, and let's see what was the actual data. All right, so let's take a look at the image, and what we're hoping to see something that looks like a 7 when I do this. Okay, and I say show me the digit, and indeed it looks like a 7. The neural network guessed it's a 7, and it's a 7, right? Are you not impressed? This, like, again, all we did was we just did some matrix operations, and we did gradient descent. Okay, again, we're not using some mystery package. We did this ourselves. We just did gradient descent here, and the computer now takes that vector of 784 values, and it's making predictions. Okay, let's take a look at the next one. The thing says it's guessing a 2, and what is the image? Yeah, that looks like a 2 to me. Okay, what's the next one? Okay, it guesses a 1, and what was the image? Yep, that's a 1. Okay, and I mean we can do this all day. All right, so the next one it guesses a 0, and indeed the digit that it you know, the image here is a 0. Okay, so so what we can do is we can just say, well, all right, make predictions for all 10,000, and let's compare the results between what we guessed and what we predicted. Okay, and so here, this is what we call this is called a confusion matrix. Okay, this is known as a confusion matrix. It shows you what we have guessed. Okay, it guesses the values between 0 and 9, and what were the actual values. Okay, so when we guessed, when the actual value was a 0, we guessed 0 962 times, but we did make a few mistakes. We guessed a 1, we guessed the number 2 once, we guessed the number 4 3 times, we guessed the number 6 7 times, we guessed the number 8 4 times. Okay. When the actual value was a 1, what did we guess? We guessed the number 1 1,113 times, but you know, we did make a few mistakes. Okay, and so basically in the confusion matrix, we want the diagonal to be big, and we want the off diagonal elements to be very small. Okay, that's what you want to see in a confusion matrix. Okay, so what I'm going to do here is I'm going to just take the sum of the diagonal and see how many values we got correct, right? There were a total of 10,000 guesses. There's the sum of this entire table is 10,000. And let's take the sum of the diagonal. All right, and so just with a very simple neural network, we're correct about 93% of the time. Okay, so it's not perfect, right? A human would do better, but again, this is a very simple neural network that, you know, has only one hidden layer with 30 nodes. Okay, and yet it's still able to achieve around 93% accuracy, which I think is something we can be proud of. Okay, and again, I hope we're able to just basically follow the entire algorithm is right here. We've just done gradient descent. We've taken our current weight matrices, which we started off with just random values. And then we just said, you know, based on what the matrix, what our neural network is predicting, right? We get some slightly, we improve our weight matrices with each iteration, and after running through our data set, you know, now we're achieving close to 93% accuracy. Okay, could changing gamma improve it? Like if you played around with that, probably. Okay, and here I also only ran through the training data set one time. Okay, so I did 60,000 images, but I did each image only once. Okay, I could have done multiple passes and things like that. You know, there's a few choices that we could have done, you know, as far as trying to improve performance. We could have made it more complicated. We could have done things. But I just wanted to kind of show that, you know, on Monday I showed you a very, very simple data set, 2 nodes in the input layer, 3 nodes in the hidden layer, 1 node in the output layer. And all I've done is I've used the same basic architecture, but I've just expanded the number of nodes. Okay, we've just expanded the number of nodes. And we can use it to now predict the number that appears in this image data set, okay? Now, you know, a few caveats again. This is a very clean data set, and so this is a very popular choice for kind of your basic computer vision tasks, but it's pretty good, okay? You know, let's, we can take a look at certain images that were misclassified, and this changes every time I run it. Okay, every time I run this. So when I first ran it, it misclassified the number 9008. It didn't misclassify it this time. Okay, but let's just take a look. 9010. Let's see. So the actual label is a 7. Our network predicted it was a 2. And let's just see what it looks like, okay? And we can say, I forgive you, network, right? The actual label is a 7, but our network predicted a 2, and we can say like, yeah, I get it, right? You're not like, it's not like, network, how dare you make this mistake? This is a forgivable mistake, right? And we will see, you know, stuff like this. So this is a lot of times the misclassification is just like bad handwriting, right? How did the human know that this was a 7? Okay, well, probably, you know, when we created the data set, like we had other information, right? It's going to say like this postcard is going to this city. We know the zip code of that city, so we know the numbers that should be appearing in that zip code and stuff like that. So, you know, so when you download the thing, this is going to probably be different just because based on the random numbers that you start off with and the training path that it takes, it's going to end up with slightly different weight matrices, and it's going to get, you know, slightly different labels. So I'm just curious. Let's take a look at image 116. Okay, so the actual label is a 4. We predicted a 6. Okay, so maybe this is a harder sell. Let's go ahead and take a look. Okay, yeah, it should be a 4, but if you told me it was a messy 6, like, you know, it's also, you know, could also pass as a 9 and things like that, right? So, yeah, and so, you know, this is basically what we're working with, right? So we've got a lot of things, and our neural network achieved 93% accuracy, which, you know, I feel pretty good about that. I feel pretty proud of our thing. Okay, probably a human could probably do better, but I'm sure. But you know, this is a very simple neural network as well. Okay, so anyway, I thought this was pretty cool. You know, as far as again, just what you can achieve with a little bit of matrix multiplication and applying gradient descent. Oh, quiz answers. I totally forgot about that. Oh yeah, okay. Let's let's do our first quiz answer. What is it? Week 3, Wednesday? Week 3 Wednesday, our first quiz answer is A as in apple. I'll give you the first two. A as in apple and D as in dog, okay? A as in apple, D as in dog. Those will be your first two quiz answers for week 3 Wednesday. A as in apple, D as in dog, okay? You're gonna write machine learning code to predict lecture viewing quiz answers. You know, so literally what I did was I just asked R to randomly sample the letters A through E. And so, you know, we can't predict randomness, right? So, yeah, if you knew the seed, maybe you could do better, but I think you need at least like a certain number of observations to try to back guess the seed, right? Which anyway, R uses the Mersenne twister, which for random digit generation, and yeah, anyway. Okay, it's not cryptographically secure, so people can figure it out after so many random values that it produces. Okay, why don't we take a break here, and then, okay, so this concludes our section on neural networks. And, you know, normally that would be it. But then, but it's summer session, so we have these 2-hour-long lectures. And so when we come back from the break, it'll be a totally different subject. I hope that's okay. But why don't we go ahead and take 5 minutes here, and then we'll come back, and then we'll continue on. All right. So we'll see you guys in 5 minutes here. All right. Is there any UCLA undergrad course that actually asks us to write neural networks from scratch? I am not aware. I don't know if anybody's taken any CS courses that deal with neural networks. I know there's one in the grad level course in the EE department that deals with neural networks and writing that, and that's all done in Python. I mean, in this class, I make you guys do some stuff, but you know, and then in your homework this week, you know, you code up a little bit of you code up some neural network stuff using a lot of, you can probably use a lot of the code that I've provided as a template to get started. And then, but then I also have you use the NNet package that, that comes with, that you can install in R, and it does a pretty good job. So it's pretty good. Okay. All right. So we will continue on here. No longer talking about neural networks. Are there any questions before I go on? Math 156 is a machine learning course. Yeah, I don't know. I don't know what happens in Math 156. But, okay, well, so now we are going to go back, take a look at least squares regression, but we're going to approach it from a different perspective, okay? We're going to approach it from a different perspective. It's still an optimization problem, but now we are no longer trying to minimize something. We're going to try to maximize something, okay? So, so when we did least squares regression, what we did was we said, okay, these are the values that we predict, right? When we take in our x values, we multiply it by our we multiply it by our weights w, right? The coefficients. And so this is either the slope and the intercept, or even if you have a higher dimensional model, it's just a linear combination, right? So it's a linear combination of these things. And so you're multiplying your input value x by w, and this produces your predicted value t hat, or your y hat, whatever you want to call it. And we said, you know, for linear regression, the weights that we choose are going to be the weights that minimize the sum of squared errors, right? Or the, in this case, the mean squared error, the difference between the actual value and the predicted value. And if we want to vectorize it, we just take the actual value minus the predicted value, which can be found by taking your matrix X and multiplying it by the weights W. And then, you know, you do T minus XW transpose times T minus XW. If you do a 1 over n, then it's the mean squared error, right? And we said, this is how we're going to pick the W. We want to minimize this. So whatever W's minimize this thing, that's going to be the W hats that we choose. Okay, so that's least squares regression, OLS. You know, we looked at a few things like regularization where we modified this loss function, but overall, this is what we're trying to do. We're trying to minimize that squared error, right? So, so to train the linear regression, it's the same approach as far as training a neural network in that we have a way to make predictions, okay? We've defined a loss function, and what we're trying to do is we're trying to minimize that loss function, okay? And so what we're gonna do today is we're gonna flip this around a little bit, and what we are going to do, instead of trying to minimize the loss, we're gonna try to maximize the likelihood of our data, okay? So we're gonna try to maximize the likelihood. And so I'm going to just do a quick review of maximum likelihood estimation. So everyone took 100B, that's a prereq for this class, and I know you guys covered maximum likelihood estimation, but then every time I asked a question about maximum likelihood estimation, in the past, you know, there were a non-zero number of students that had forgotten or, you know, missed certain key ideas here. So I'm going to do a quick review here, and maybe you already know all of this. Maybe this will be a good review to have. So anyway, this is stuff that you should have seen before, but I'm going to just go over it here again, okay? So what we're going to do is we have a model, a generative model for our data, okay? So we're going to say our data, the data that we've observed, is the result of a random process, right? It's some kind of process that includes random noise, right? So in a linear regression model, the generative model looks like this. You've got the true value, the true quote true value, mean value is something times W times X, but then there's always some random noise, epsilon, okay? Epsilon represents some random noise, okay? And the key difference here is that when you did, when we were doing minimizing the loss, you know, T hat was the result of W times X, okay? Now we are just saying we're gonna add a noise term. And this is truly the difference, the only difference that really matters, right? So the actual value is gonna be the predicted value T hat plus random noise, right? So the actual value is the model prediction plus random error, okay? And by having that random noise, our model is now a probabilistic model, okay? Our observations, the observations that we see, because there's this random noise, we can say our observations come from some probability distribution. And if it comes from probability distribution, then every observation has a likelihood associated with it. And now what we can do is we can select the model that will maximize the likelihood of our data, all right? And this is what we want to do. We want to be able to maximize the likelihood of our data, because every observation that we have now has a likelihood or probability associated with it, because we have a probabilistic model behind the generation of this data point. I'm hoping this is okay. I'm hoping this is okay so far. All right, so the key assumption for least squares regression, okay, or for linear regression, often is that your noise, your random error, is normally distributed with a mean of 0, right? So generally, if you take a linear regression course and you have to check your conditions, you know, you check the model assumptions is what you're supposed to do after the fact, right? You fit your model and then you find the residuals and you check your residuals to see if they fit the model assumptions. And I don't know if anybody explained it, but they just said, you know what, we're gonna assume that that they're normally distributed, that there's constant variance. And we just kind of accepted that and said, all right, That sounds reasonable to me, and we went with it, okay? And so that's what we're going to put here. We're going to say epsilon, we're assuming comes from a normal distribution centered at 0 with constant variance sigma squared, okay? So if this is the case, right, if we're saying the actual value is our prediction t hat plus epsilon, we can turn this and say the values that we observe, t sub n, come from a normal distribution where the mean is W transpose XN, right? This is the true value, okay, W transpose XN, where with a variance term, sigma squared, okay? So if we were able to kind of turn the values that we have from taking this mean function plus adding some random noise into saying the values themselves come from a normal distribution with this mean, okay? Is that all right? Combining this with this to get this, okay? So now we can say our observations t sub n come from a normal distribution. Now they are governed by a probability distribution, okay? The only thing here is that this mean, W transpose XN, depends on the XN value. It's not a constant. It's not like just the normal distribution centered at 5. It's a normal distribution, but centered at different locations based on the X, okay? So the picture looks like, so maybe we're doing linear regression, sorry for my crude drawing here, is that this is, you know, these are the random values that we've seen, okay? And the idea here is that, I don't know what happened here, but the true values, the true relationship is this blue line, okay? And the random values we see are effectively, you know, for this particular X value, this is the mean, and the values that we observe come from a normal distribution centered at this thing, okay? For X's of this particular value, this is the mean that we expect, but when we get random values, they come from a normal distribution centered right there, okay? And so this is what we are, what we're doing, okay? The observations themselves are normally distributed, but they are not normally distributed around a constant. They are normally distributed around a function, okay? And in this case, it's a linear function, which is W transpose XN, but this function here, because it's just a linear combination of multiple values, right? If you have a high dimensional model, you know, the mean function could be some kind of surface or hypersurface, and then the observed values themselves are still normally distributed around that function here, okay? And we're assuming constant variance, right? And that assumption of constant variance is frequently violated. You know, as far as linear regression goes, we don't, there's a few things you can do to handle heteroscedasticity, but we just say, oh, I sure hope I don't run into that problem, you know, because this is kind of the model that we're assuming here. All right, so what we have is we have a probabilistic expression for observing for each observation in our data. And what we'd like to do is we want to select our model parameters so that we maximize the likelihood of observing the data we have. Okay, let me just pause here. Did you guys already do this in 100B where you did maximum likelihood estimation for linear regression, or was it like maximum likelihood estimation for the mean? Okay, no, okay, so you have not done this. All right, okay, well, good. Well, I don't know, all right. So you did MLE for regression in 100C. Oh, I see, okay, 100C, all right, well, okay, so there's gonna be a little bit of overlap here. Okay, like a week or so only. Yeah, I mean like a week or so only here also, okay. Okay, all right, so my apologies, there's gonna be a lot of overlap between this and 100C, okay? That's all right, it's okay to see the same thing more than once in your undergrad education from slightly different perspectives. Okay, so for maximum likelihood estimation, the idea here, when you do maximum likelihood estimation, is we want to maximize the likelihood of your data, okay? And so, so this is a completely different example, just to say the idea is we treat our data as fixed, okay? And by treating our data as fixed and the model parameter as the, or the function as a function of the parameter, we can maximize that likelihood function, okay? So the probability function of observing some value x given some parameter theta is this. This is just a generalized function, okay? And so if we have a Bernoulli distribution, right? So let's say we've got this, I don't know, you have some kind of pouch, and inside the pouch there's marbles, and all right, so I've got some marbles here, and then we're gonna put them in the pouch, and what we're gonna do is we're gonna draw one of the pouches, one of the marbles out, and it's blue, okay, or whatever, or it's red or something, and we put that in, we shake it up, and then and so every time we draw, because I'm putting the marble back in here, it's a Bernoulli distribution, right? Okay, and then you get a different colored marble or something like that. Okay, so so that, that's what we're trying to do here, and so we're going to say the probability of drawing a red marble is 0.3. Okay, if we got 3 marbles are red out of 10 marbles on the pouch, we're going to say the probability of drawing a red marble is 0.3. It's a Bernoulli distribution. Bernoulli has this probability mass function, theta to the x1 minus theta to the 1 minus x. Okay. Now, let's say I want to do what is the probability of drawing the following sequence, red, red, blue, okay? Here, I would just multiply the probabilities of these outcomes, right? So I take my PMF and I say the total probability, if we're assuming all of these things are independent, the total probability of the sequence of events, red, red, blue, is going to be the product of all of these things. So I just do 0.3 times 0.3 times 0.7, and I get 0.063, okay? And this is a little bit different from a binomial probability because it's asking for this exact sequence of red, red, blue, and it's not saying I want 2 red and 1 blue in any order. It's saying for this exact sequence of red, red, blue, which is what we're having. Okay. The difference between probability and likelihood, okay, they both describe probabilities, but the key difference here is that a probability function, a density function, or a probability mass function is a function of the different outcomes x. You plug in, you say, what, I'm going to plug in this value x. What is the probability I get this particular outcome? And what's that probability? And in that case, the parameter theta is fixed, and you change the outcome, and then the result of these probabilities have to add up to 1. Okay, either the area under the curve, if it's a probability density function, must integrate to 1, or if it's a probability mass function, the sums of the probabilities must add up to 1. Okay. A likelihood function, on the other hand, is a function of the parameter theta. Okay. The observed data x is treated as fixed, and instead you are manipulating the parameter theta. Okay. And a key difference is that a likelihood function will not integrate or sum to 1 over all the different possible values of theta. So you can consider all the different possible values theta can take, but it is not necessarily going to integrate or sum up to 1, okay? Whereas a probability mass function, you take all the different outcomes that x can take, and that will add up or integrate to 1, okay? They both describe probabilities though, but there's a difference between these, okay? All right, so as far as the pouch with the marbles, okay? If we drew these 3 marbles and get this sequence, red, red, blue, okay? And we call red 1 and blue 0, we can ask, well, what is the likelihood function? Okay, what is the likelihood of this particular outcome? Okay, So this time the function is a function of theta, and we're going to treat the observations of red, red, and blue as fixed, okay? And so the likelihood is the product of the probabilities, okay? And in this case, we have x is 1, 1, and 0. And so the product of all of these things will be theta squared times 1 minus theta, okay? So whatever theta is the probability of getting a red one. The likelihood of that is going to be theta squared times 1 minus theta. So if the probability of getting red is 0.5, then we would do this, okay? If there's any difference, yeah, sure, we can watch this video, or you can watch that. Yeah, there's a subtle distinction between the likelihood and the probability, in that one is treated, one we treat the parameter as fixed, and the other we treat the data as fixed, okay? So as far as this likelihood function goes, we are treating this sequence of outcomes, 1, 1, 0, as a fixed thing, and we are going to say we can manipulate, or I don't know, we'll allow the parameter theta to be different, okay? And so, so if theta has a probability of 1, right? Like if we say the probability of getting a red is 1, then the likelihood of this outcome of red, red, blue is going to be 0, because it's going to be 1 times 1, 1 squared times 1 minus theta. Theta is 1. So 1 minus theta will be 0. So it's going to say it's impossible to get red, red, blue if the probability of getting red is 1, okay? On the other hand, if the probability of getting red is, say, 0.9 or 0.1 or something else, you get a different value, right? And so you can, we could graph this ourselves, but we could just ask this question: what value of theta maximizes this thing, right? What value of theta maximizes this likelihood, okay? So, this is just one strategy to estimate the parameter, and that's to maximize the likelihood associated with observed data. And so we just want to say, well, what value of theta is going to maximize this, okay? So how do you maximize a function? Well, often you just take the derivative, set it equal to 0, and solve, okay? But taking the derivative of a product can get messy, okay? So especially if you have a big product. So what we often do is we will deal with the log, okay? And so you'll often see log likelihoods rather than the likelihood function itself, okay? Because taking the derivative of a product can get messy, okay? So when you turn it into a log, the products become sums, okay? That's what the log does. And so the log of the likelihood turns, theta squared 1 minus theta into, 2 log theta plus log of 1 minus theta, okay? And now we can take the derivative of this, set it equal to 0, and solve, okay? And the nice thing about the log function, okay, is that whatever value maximizes the log likelihood is going to be the same value that maximizes the likelihood itself, okay? Because if for all A and B, where A is greater than B, log of A is always going to be greater than log of B. So, so you're still a little confused how minimizing and maximizing are different. Well, so what we are doing is the same, right? Mechanically, the process to find the critical points using calculus are the same, okay? It's basically you minimize and maximize in the same way, in that you're trying to find the spot where the derivative equals 0, and it's just that at the maximum it's concave down, and at the minimum it's concave up, okay? Or you can do a few other checks to do this, okay? So anyway, I don't know, I hope that's okay. So we take the derivative of this, and okay, so derivative of 2 log theta, right? So it's going to be 2 over theta. Derivative of log of 1 minus theta is 1 over 1 minus theta, chain rule multiplied by the -1. And we get this, and we're going to set that derivative equal to 0, and then we solve for theta. So solving for theta, you get theta is equal to 2/3, okay? And so that is going to be the value of theta that maximizes this function. When theta is equal to 2/3, this likelihood function is maximized. At any other value of theta, you're going to get a slightly smaller likelihood function, okay? And theta, if we think about it, can technically is a continuous value, can technically be any value between 0 and 1, okay? Can be any value between 0 and 1. And it's continuous, and here we get 2/3. All right, so so this is just kind of the idea of maximizing the likelihood, and that's maximum likelihood estimation. We treat the observed data as fixed, and we're going to try messing around with our theta parameters to see if we can maximize the likelihood. Okay, so when we do this with linear regression, okay, we've left off and we said, you know, our values, the observed values Tn, come from a normal distribution. The normal distribution is centered at W transpose Xn, and it's got this variance sigma squared, okay? And so if we assume all of our observations are independent of each other, the likelihood, the total probability of our data is just going to be the product of the probabilities, right? So we'd say, what's the probability of getting this particular observation T sub n, okay? And we're going to have n of these things, and we're just going to multiply all of these things together, all right? And so, so the question here is, so in this case, changing theta would be like changing the proportion of marbles in the pouch, which of course is fixed in this theoretic example. Perhaps that's part of the reason why MLE can be intuitively confusing. Yeah, okay, so yes, changing theta is changing the proportion of red marbles in the pouch, okay? What's going on is we don't know what's inside the pouch, okay? Is what's inside the pouch 50% red? Is it 99% red? Is it 100% red? Is it 20% red, okay? And all we've done so far is we've drawn 3 marbles out, okay, with replacement. We got 2 red marbles and 1 blue marble, okay? And we're saying, based on that, what do you think is the proportion that's red in here, okay? And so we're just playing this theoretic game, this hypothetical game that says, well, what if the proportion of red marbles is 100%? What is the probability that I would get 2 red and 1 blue? And we go, well, it would be impossible to get that blue marble. So having 100% red here would have a likelihood of 0, okay? What is the probability I would get 2 red and 1 blue if it was 0% red? Okay, if it was 0% red, that would also be impossible. So the likelihood of my data, 2 red and 1 blue, would be quite low, okay? What if it was only 1% red? If it was 1% red, it's theoretically possible to get 2 red and 1 blue, but it's a very low likelihood because I would have to get 2 red. Each red only has a 1% probability, okay? So it's very low, okay? And on the other hand, if I'd say if it's 99% red, well, the reds are easy, but then how did I get that blue? That blue only has a 1%. So it's gonna be very low, right? And so you can try all of these different theoretic or hypothetical values for what proportion is red, and it turns out that the proportion of red that is gonna maximize the likelihood of the data, where you get 2 red and 1 blue, is gonna be 2/3 red, okay? 2/3 red strikes that balance where you want more reds than blues, okay? But you also don't want the probability of blue being so low that the fact that you did get a blue isn't gonna totally knock it out, right? Because if we said it was 99% red, you can say, all right, that explains the 2 reds that I saw, but how do you explain that blue? Like, it's possible, but only a 1% blue, it seems low. So it's just, yeah, we're playing this hypothetical game of like, what proportion can I mess around with, and what proportion of red in this pouch that I can't look inside directly, what proportion is going to give me the best, okay? That's what we want. All right, and so we're taking that thing, okay, except now we're not messing around with a pouch anymore. We're messing around with this data, okay, where we're saying, here's the data that I've observed, and what is the blue line? What blue line is going to maximize the data that I've observed, right? So we want a blue line that kind of threads the needle and goes straight through the kind of the middle here. Okay, if I pick a blue line that goes like this from the lower corner up to the other side, that's probably not going to be a good one, because the data there is going to be very unlikely to happen. Okay, so so I'm just using the rules of probability here, which says, you know, if you've got a whole bunch of independent events, the total probability of that sequence is the product of all of those things, right? So here is just the general form of saying the observed value is t, and these are the parameters. The parameters that we can mess with are going to be w, and actually we're going to just mess with w. Okay, we're going to treat our observed values x as fixed. We're going to treat our sigma squared as fixed in the beginning. Okay, we're going to just start there. Okay. And then, and in this case, if it's normally distributed, what we're going to do is we're going to use the PDF of the normal distribution here. Okay? We're going to use the PDF of the normal distribution. Okay. So the PDF of the normal distribution is this thing: 1 over square root of 2 pi sigma squared e raised to the negative x minus mu quantity squared over 2 sigma squared. You don't have to memorize this, but if you're going to call yourself a stats major, you should have something of this. The key, all right, if you forget the constant here and the constant here, the key is that you've got e raised to the negative x squared. Okay, you've got e raised to the negative x squared, and that's going to give you something to the that looks like the normal. True pros memorize the chi-squared PDF. Sure, yeah. So anyway. This is all I'm going to do, okay, is I'm going to just take the normal PDF and I'm going to just plug it in for this, okay? So the total likelihood is going to be the product of all of the normal PDFs for the different observations that I have, right? So the observations that I have, okay, is going to be, right, I've got the x minus mu squared, okay? The observed value that I have is actually t sub n. And then the mean, this is a little weird, the mean is the result of doing w times x sub n, okay? So this is going to be the product of all of the normal PDFs, okay? So I extracted out the sigma squared to 1 over sigma root 2 pi e to the negative, and then each observation t is the kind of our observed value minus what the mean is, okay? The mean is W transpose xn, okay? And what we want is we want to say, well, what value of W is going to maximize this total probability here? What value of W will maximize the total likelihood of our data? Okay, so this is, again, the likelihood function is a function of, in our case, we're going to do W. We're going to start with W. We're going to treat everything else as fixed and constants. We're going to treat this variance sigma squared as a constant. Technically, that's a parameter of our model, but we're going to just treat it as a constant. We're going to treat the observed values t as fixed values. We're going to treat the observed values, the input values x as fixed values. Everything is fixed. The only thing that we're going to mess around with is W, okay? We're going to hypothetically mess with the W. We're going to twist the knobs and we're going to say, well, what if I increase W this way or decrease W this way? And remember, W itself is a vector. Okay, so we're going to try messing around with the W's here and say, well, what value of W is going to maximize the likelihood, which is the product of all of these probabilities. Okay, so what we want to find the values of W that are going to maximize this entire function. Okay, well, well, when you did it in 100C, did you use vectors or did you use partial derivatives? Nobody remembers? You guys, but you said you did it in 100C? Yes, okay. Oh, okay, and you did it for beta 0 and beta 1. So you did partial derivatives. Okay. Well, here we're going to do it in vector notation, okay? Which will allow us to generalize to beta 0, beta 1, beta 2, beta n, right? Okay, so we're going to do it in vector notation. All right, so this is our likelihood function. And I'm going to take the log of this thing, all right? So I take the log of the likelihood, it turns the product into a sum, and then 1 over sigma square root 2 pi, okay? The 1 over sigma becomes negative log sigma. The square root 2 pi is going to become log of 2 pi raised to the negative 1/2, right? Square root 2 pi is 2 pi raised to the negative 1/2, so that becomes negative 1/2 log of 2 pi. And then this thing, because of the log cancels out the exp, so now I just get this, okay? And so I'm gonna, and if we do sum from 1 through n, these are constants, so we're gonna just have n of these constants. This is a constant, so we're gonna just have n of these constants. And then this is not a constant with respect to n, the x of n, that's gonna alter. So we have to keep that as a summation, okay? So the solution that maximizes the log likelihood will be the same value that maximizes the likelihood function. We're gonna take this log likelihood, we're gonna take the derivative of it, set it equal to 0, and solve. Okay, we're gonna take this, this is the log likelihood, we're gonna take the derivative of it with respect to what? With respect to w, because that's the thing that we're altering. Okay, we're gonna take the derivative of this with respect to w, set it equal to 0, and find the w that maximizes our log likelihood. Okay, so this is our log likelihood function. So this, I just copied this, whoops, this is what we have here. We're gonna take the derivative of this with respect to w, okay? So this is a constant with respect to w, it's a 0. This is a constant with respect to w, it's a 0, okay? And then now, I've got the sum of this, and then, so the square comes down and cancels that out. And then I apply chain rule. So I've got t minus w transpose xn, and the derivative or the gradient of w transpose xn with respect to w is this, negative x to the n. Now that we're dealing in matrix notations, you should always write your dimensions underneath to kind of make sure you're not messing things up. Okay, so this negative x is going to cancel out this negative, so I just drop that here, and I've got the sum of x of n, which is a 2 by 1 thing, if I'm assuming x is two-dimensional, but you know, maybe it's higher dimensional, it doesn't matter. Okay, t sub n is 1 by 1, w transpose xn is also 1 by 1. Okay, and what I can do is I'm going to transpose w transpose xn into xn transpose w, right? So a scalar transpose is equal to itself, and that's going to just simplify, help out my work here. And then I'm going to go and distribute the x sub n's here, okay? So now I got xn times tn, and then I got xn transpose w. All right, hope that's okay so far. All right, so this is what I have, 1 over sigma squared sum of xn tn minus xn transpose w, which is what I have here, xn tn minus xn transpose w, okay? And I am going to group up the summations, okay? So, or distribute the summation. So I got 1 over sigma squared times the sum of xn tn minus the sum of xn transpose w, okay? So I'm just kind of working through this. All right, so let's keep in mind what is each xn. Each xn is this, and the entire matrix X itself is each xn transpose. Okay, so X is this, and T, the matrix T is all of these things, and W is, you know, W0 and W1, but it can be generalized to something greater. Okay, and so, well, what is the sum of x and tn? Okay, the sum of x and tn, if I expanded the x's to the full matrix X and the tn's to the full matrix T, the sum of x and tn is just X transpose T. Okay, and you can take a look, and if you did all of the multiplication, well, what is this times this? Okay, yeah, it's going to add up to this. Okay, X transpose T. And then what is, if I try to get rid of the sum here by using matrix notation, xn transpose W can be simplified to X transpose XW, okay? And so you can take a look, right? If you do each of these things, 2 by 1 and 1 by 2, is going to form a 2 by 2, and if I use the full matrix X and I do that multiplication, it's going to sum it up into a 2 by 2 matrix as well. Okay? And then we multiply that by W and we get to 2 by 1. And so, so here, the the derivative of the log likelihood function with respect to W is 1 over sigma squared X transpose T minus X transpose XW. Okay, we're going to set that equal to 0. Okay, and solve for W, and I kind of shortcutted this, but I think you guys can see that if I set this equal to 0, then we're going to have X transpose T. I'm going to multiply both sides by X transpose X inverse, and we get W hat is equal to X transpose X inverse X transpose T. Okay, and this is the exact same solution that minimizes the sum of squared errors and mean squared error, right? So the W hat that maximizes the log likelihood is also the exact same W hat that minimizes the sum of squared errors and mean squared error. Okay, and this all comes from basically the key here. The key assumption is that if the errors are assumed to come from a normal distribution, which formed the basis for the likelihood function that we're using. Okay, if we assume the errors follow a normal distribution, then this is our likelihood, and then the natural kind of conclusion of that is going to be this. So if the errors are assumed to come from a normal or Gaussian distribution, then minimizing the squared loss is exactly equivalent to maximizing the likelihood. Okay, so we maximized the likelihood, and we came to the exact same conclusion that minimizing the sum of squared errors and mean squared errors does. Okay. The variance sigma squared doesn't appear in the solution W hat at all, okay? Which means that whatever variance we have doesn't affect the W hats that we end up choosing, okay? Which is kind of an interesting fact. As long as you're assuming this sigma squared, your variance, to be a constant, what you observe is unaffected. I just kind of, so this idea of the minimizing the sum of squared errors is equivalent to maximizing the likelihood might be a little surprising, but take a look at this, okay? When you do the likelihood function, okay, this is the normal PDF, right? This is basically the product of the normal PDFs. And when you take the log of this likelihood, okay, the log of this likelihood, what do you get? You get all of this stuff over here becomes constants, okay? This thing turns into a negative constant, okay? And then because we've applied the log function to a product, we get the sum of basically this inner part here, okay? And so take a look at that. This is the sum of squared, this is effectively the sum of squared errors term, the sum of squared errors term. It's being multiplied by a negative constant, okay? And so the reason why maximizing the log likelihood is the same as minimizing the sum of squared errors is because we are trying to find the W that's going to maximize this. It's being multiplied by a negative constant. So if we want to maximize this, we want this to be as small as possible, okay? Because this is being multiplied by a negative. So so this is the sum of squared errors. If we minimize this, that's going to maximize the log likelihood. And so I think that's kind of a, it's not, I don't know if it's obvious at first glance. When you see this likelihood function, it just seems like, oh my goodness, there's just a whole bunch of like PDFs and all of this stuff. But if you just kind of break it down a little bit, you know, just the fact that when you use the normal distribution, the Gaussian distribution, the sum of squared errors is present in that log likelihood. This is the sum of squared errors here. And so if you wanted to maximize the likelihood, you've got to minimize this thing because it's multiplied by a negative constant. Okay, so so anyway, this is the point of this lecture is just to kind of show that you know, it's still an optimization problem in that we're searching for a minimum or a maximum. and even if you take a generative approach to the data, okay? So you're not just taking, you know, here's our values and here's our predictions, and let's try to shrink the difference between our values and our predictions. But let's say you're taking now a probabilistic approach and saying our data is being generated by some probability distribution. You can maximize the data that way using maximum likelihood estimation, and it's kind of a neat thing that they work out the same. Oh, the last quiz answer. Thank you guys. What would we do without you reminding me? If this was like if I did pre-recorded lectures, we'd be in trouble, right? Okay, the last quiz answer for week 3 Wednesday is B as in bear, B as in bear, B as in ball. So B as in bear. Okay. Oh, the first two, you didn't hear them. Okay. I'll put them in the chat right here. Okay, those are the first two. All right. And we will end there for today. Good luck as you guys study, and we will see you guys on Friday for the midterm exam. So see you then. Have a good day. Good luck as you study. Oh yes, and I will have office hours tomorrow at 1. So our class time office hours will be at 1. Okay, we'll see you then.